Hello students, welcome to this module, which is part 3 in our discussion on mathematical preliminaries that are required for the course Introduction to Hydrodynamic Stability, CHE 614 at IIT Kanpur. Now, in the previous two modules, let me briefly summarize what we had discussed in those previous two modules. First, we looked at finite dimensional spaces, wherein a linear transformation takes the form m times, suppose you have any vector a and any linear operator m, so ma is b. Okay, so this is an example of a linear transformation if m is a linear operator. Okay, now if I express this in any basis, in any given basis, what I will get is a set of coupled equations. M11A1 is B1 and M12A2 plus M21A2 plus M21A1 plus M22A2 is B2. So these are a set of linear equations that are simultaneous or coupled. Okay, now this is the case if you have any arbitrary basis, but the idea is if you were to use the eigenbasis of the linear operator or use the eigenvectors of m as the basis for expressing a and b, then what you will find is that you can expand a. Let the eigenvalue problem be m ei is equal to lambda I ei, where ei's are the eigenvectors and lambda's are the eigenvalues. Okay, now if I were to expand, now although I had given this example in the case of 2 dimensions, this is true for any finite dimensional space. This is true for n dimensions as well. Okay, just for the sake of clarity, I've written 2 dimensions. So you would expand. Suppose you were to solve, you are interested in solving ma is equal to b, in the sense that you are given the b vector and you want to find the a vector. Now what you can do is you can write a as some constants ai times ei, where ei's are nothing but the eigenvectors of the linear operator m. Okay, right, these are the coefficients that are unknown, whereas the eigenvectors are known. So essentially if you find these constants, it's as good as finding a. Right, now so what we'll do is we'll substitute this back in this expression. So we'll say m times summation I ai ei is equal to b. Okay, now because it's a linear operator, I can take the operator inside the sum, so I can say summation I ai mei is equal to b, but mei is lambda I ei from the, because that's ei's are eigenvectors, so this will become summation I ai lambda I ei is equal to b. Okay, now if I assume ei ej, the dot product of the two vectors, so let's use the same symbol that we used, notation that we used for dot products. Ei dot ej is delta ij. They are orthonormal eigenfunctions. They are orthogonal and they are normalized such that when they are dotted with themselves, they give you 1 or unity. Now if that is the case, then I will dot this equation with ej, right? Then I will get summation I ai lambda I. Now I will get ei dot ej, which is delta ij. Okay, which is b. Now whenever I have a delta function, this is a Kronecker delta, so delta ij is 1 if I equal to j, is 0 if I not equal to j. Okay, now this means that I is the running index here, j is the fixed index. So whenever j is the index that you are giving, so whenever I equal to j, this will give you 1, otherwise it will give you 0. So this will simply give me, okay, now I have to dot the other side also with ej. Okay, this will simply give me aj lambda j on the left side. Now b dot ej, if you imagine the vector b to be expanded in the eigenfunction bases themselves, okay, sometimes something like this, then b dot ej will also be bj. So lambda j's are known, bj's are known because b is a known vector. So the unknown coefficients are given by simply bj by lambda j. Okay, essentially in the eigenbasis, eigenvector basis, the system of coupled equations ma equal to b get decoupled or we say we have diagonalized the matrix M. Okay, so this is the idea that we followed for finite dimensional spaces. Now we can do something very analogous for infinite dimensional spaces. Let L be a linear differential operator. Okay, L can be something like minus d squared by dx squared, for example. This is just an example. L can be any linear differential operator. Okay, now suppose you want to solve, let's say L u is equal to some function f. This is known, and with some boundary conditions, u of 0 0, some u of L is 0, something like that, for example. Okay, the key idea is that the boundary conditions need to be homogeneous. We can tackle inhomogeneous boundary conditions, but I will not get in there. You can use the notion of linearity to and superposition to solve inhomogeneous boundary conditions as well, but let's not spend time on that in this particular course. Okay, now imagine you want to solve this. First, so in order to solve, use the method of eigenfunction expansion. First solve L, let's call the eigenfunctions phi j lambda j phi j subjected to phi j of 0 is 0 and phi j of L is 0. Okay, now this is the eigenvalue problem for the differential operator. This is the eigenvalue problem for the differential operator. Once you solve that, then in principle you should get a set of orthogonal or linearly independent eigenfunctions and distinct eigenvalues usually. Okay, let's assume that such is the case here. Now I can expand the unknown function. Okay, to when I say to solve, you should understand that this is the unknown function. This is like a differential equation that needs to be solved for u, right? The unknown function u of x can be expanded as some ui coefficients times phi I of x. Okay, these are known because we have solved for them from here, and these are unknown. Okay, now what I will do is I will substitute this back in this problem. Lu is equal to f. Okay, let me just make some space here. So L u is f. Instead of u, I am going to substitute 1 to n ui. This is ui is equal to f of x. Okay, now this is nothing but, since L is a linear operator, you can write I is equal to 1 to n. This is coefficients ui times L phi I of x is f of x. Now L phi I, because it's phase or eigenfunctions, L phi i's are nothing but lambda I phi I or lambda j phi j depending on the index. So this is I equals 1 to n ui lambda I phi I is f of x. Now if the eigenfunctions are orthonormal, phi I phi j dx 0 to L is delta ij. I am assuming orthonormal eigenfunctions. Okay. Usually you have an orthogonal set of eigenfunctions. You can normalize them by suitably multiplying them so that you get unity when you multiply an eigenfunction by itself and integrate from 0 to whatever the domain is. Okay. So I am going to take this expression and multiply by phi j and integrate from 0 to L dx, the entire equation. Okay. Once I do that, I'll find that you have summation I equal to 1 to n ui lambda I. Then you will have this kind of an expression. You will have integral phi I phi j dx, which is delta ij, is nothing but integral 0 to L. On the right side you have f of x, you have phi j of x dx. Okay. Now this is nothing but this is a Kronecker delta, so it will pick out only uj lambda j from this summation. So this is, you can think of this as the, if f was to be let me just take one extra step. If f were to be expanded in the same eigenbasis fi phi I, and if I substitute this here, then these are known coefficients. Okay, so you can say that uj, from here it's uj lambda j, is, again you will have a delta function. This is fj, so uj, the unknown coefficients, is nothing but fj by lambda j. Now if you look at or compare what we had done for the finite dimensional case, which is m a is b, and the infinite dimensional case L u is f, where L is a linear differential operator, here m is in some sense a matrix operator. If you look at the steps involved and the final results, they are almost identical. What is different, or what distinguishes the two situations, is that in one case you have to solve the eigenvalue problem, which is a differential eigenvalue problem. In the other case you are trying to solve a matrix eigenvalue problem out here. Okay, this is a matrix eigenvalue problem, whereas this is a differential eigenvalue problem. In that you have to solve a differential equation. That is the only difference between these two cases. Okay, so this is how one solves a system of linear equations using the method of eigenfunction expansions. Now this is something that we covered in the last couple of modules. This is just a quick summary so that you get a sense of how unifying the procedure is, how general the procedure is. Right, now let's make some more generalizations on eigenfunctions. Okay, now the dot product of two vectors, is defined in a given basis as summation ai bi in a given orthonormal basis. Is simply ai bi, right? Now the generalization of dot product in eigenfunction is called the inner product or scalar product. Okay, so if you have two functions f of x, g of x, the inner product is defined as, or the notation is given by fg. Okay, now I am going to now assume that f and g can be complex valued in general. in the previous module we discussed real valued eigenfunctions. If f and g are in general complex valued and they are defined in a domain between a and b, then the inner product is defined as the complex conjugate of the first function times the second function appearing as such times dx integrated over the domain. This is the complex conjugate of the first function. Example, if f of x is e to the 2ikx, then f, the complex conjugate, is e to the minus 2ikx. Okay, so this is how eigenvalues, scalar or inner products are defined for complex valued functions. The reason why we are using this is because if I take the inner product of f with itself, then by our definition you will get f bar f dx. Now this is nothing but if you multiply a function by its own conjugate, then you will get its modulus squared. So this is real valued. You want in some sense the inner product of a function with itself to be real valued. To demand that, or to ensure that, you make sure that the first entry appears with a complex conjugate. Okay, so this is in some sense f to the half is like the length or norm of the function f, in as much as you have, if I have a dot a whole to the half is the length of, if a represents physical distances, this is the length of the vector a, right? In much a similar manner we define inner products of functions as well. Okay, now if I have a set of eigenfunctions, okay, ekx, okay, now in an interval a to b, then ek in general is defined as a to b ek of x. The first entry comes with a complex conjugate. In general, one has what is called a weighting function in the definition of inner products. Okay, usually for Cartesian coordinate systems this is unity, but in other coordinate systems you will have some function times dx, and if in general if I multiply an eigenfunction with itself, it will give you some number, a real number, because you are multiplying the function by its conjugate and integrating. But if you have normalized this function to unity, then the inner product of a function with itself will give you unity. And if the functions are orthogonal plus normalized, they are called orthonormal, in the sense that if I take ei, ej, which is nothing but a to b, ei of x, ej of x, s of x dx is equal to delta ij. Okay, so if the functions are orthogonal, the eigenfunctions are orthogonal, and they are normalized, they are called an orthonormal set of eigenfunctions. Now any function f in the same domain and satisfying the same set of boundary condition as ei's, it can be expanded as in terms of the eigenfunctions as some I equal to 0 to n fi ei of x. Okay, and this is the basis of Fourier series, for example, but more generally this is the expansion of a function in terms of orthonormal eigenfunctions is called eigenfunction expansion. Okay, now the moment you expand, then you can ask the question, what are the coefficients fk? So fk is nothing but you take the inner product of this with ek. Okay, then if these are orthonormal, then if the inner product will give you delta ik, and that summation will pick you just fk. Okay, so what I'm trying to say is take ek, take inner products on both sides of this equation with ek, so you'll get I fi ek ei, but ek ei is nothing but delta ki, and delta ki of fi is nothing but fk. Okay, so that's what is written here, that the coefficients of expansion are obtained by taking the inner product of the function with the particular eigenfunction. This is very similar to if I have a is a1 e1 plus a2 e2. Now what is a1? You will say a1 is e1 dot a. What is a2? It's e2 dot a. In general, ai is ei dot a. This is the same thing that's happening here. This is the same thing that's happening here as well. These two are equivalent. This is single dot, I'm sorry, a dot a. This is in finite dimensional space. This is in an arbitrary infinite dimensional space. Okay. Now, if I have two different functions, f1 and f2, then okay, instead of f1 and f2, let's call the functions as f of x and g of x. Then the coefficient of expansion of f of x, both of them can be represented in the same eigenfunction basis. That's a summation over I. Okay. Now, in general, gi's are not equal to fi's in the given basis unless and until f and g are the same functions. Okay. So, in general, two different functions will give rise to two different set of coefficients. Okay. Now, one last relation, which is called the Parseval's equality. Okay. Suppose I take f and take the inner product with itself. What we just said is that this is nothing but the modulus of the functions f squared at each point multiplied by the weighting function. This is nothing but the conjugate times f dx. So now what I can do is I can write, instead of f bar, I can expand this in terms of fj ej of x whole bar times k fk ek of x times s of x dx. Okay. Now I can interchange the sum and integral. So this is j k fj bar fk a to b ej bar ek s of x dx. Now if this is a bunch of orthonormal eigenfunctions, this is this is e. Okay. This will be delta jk. Okay. So f inner product of f with itself is nothing but j k fj fk times delta jk. So this is going to, the delta, Kronecker delta is going to kill one summation. So to give summation over k fk f bar k times fk, this is nothing but mod of fk the whole square. Okay. This is called Parseval's equality. The inner product of the function with itself is the sum of the square of the magnitudes of all the coefficients. Now this is not something that's very unique, because if I take a vector A in 3 dimensions, a1 e1 plus a2 e2 plus a3 e3, and let's assume that the unit vectors are orthogonal, then a dot a will be a1 squared plus a2 squared plus a3 squared. This is summation over I or k ak squared. Again, you can see the similarity. The Parseval's equality is merely a generalization of this to a function space, but the final result is the same provided the eigenfunctions are orthonormal to each other. Okay, so this is a good point to stop this module. In the next module, we will proceed to see how we will try and solve partial differential equations using the method of eigenfunction expansions. Thank you until then.